Okay, yeah, thanks, Yao. So good morning and good evening. So my name is Chaoxiang Zhu. I'm from USTC. I'm delighted to welcome you all to this special colloquium co-hosted by Shanghai Jiao Tong University and University of Science and Technology of China. So we have an exciting agenda ahead. It's my pleasure to introduce today's speaker, Professor Egemen Kolemen. So Professor Kolemen is an associate professor at the Princeton University's Mechanical and Aerospace Engineering, jointly appointed with the Adlingo Center for Energy and the Environment, and also the Princeton Plasma Physics Laboratory. So he's the director of the program in sustainable energy, recipient of the David J. Rose Excellence in Fusion Engineering Award, and ITER Scientist Fellow. His research combines engineering and physics analysis to enable economy feasible fusion reactors. He currently leads research on machine learning, real-time diagnostics, and controls at K-Star, NXTXU, and D3D. He directs liquid metal diverter and low temperature diagnostics labs. On the theoretical side, his group develops software for stellarator optimization and economical analysis of fusion reactors. So today, Professor Kolemen will present some groundbreaking research conducted by his group, which was recently published in Nature and has garnered significant attention. So the title of his presentation is Avoiding Fusion Plasma Telling Instabilities with Deep Reinforcement Learning. Okay, so with that, I will hand the mic to Yao or Eggman.
Thank you, Shelley. So yeah, I kind of kept it a bit more broader than just a single paper. We have a big group, so on the machine learning side, about a third of our work is on machine learning side. I work with you, as you know, on stellarators and other work. So I'm going to talk more generally about machine learning for fusion. And okay, so we have a chat here. Oh, okay, it's on that side. Okay, all right. So for those of you who are not familiar, fusion is the main source of energy in the solar system, well, and in the universe for that matter. And here's sun, and you know that there's fusion energy being produced inside the sun, which gives out the heat and the radiation that heats the earth. It powers our solar powers, and wind is a source of fusion that's converted to circulation. And even the fossil fuels, if you think about it, they were fusion energy that has been stored for millions of years. So all the energy that we use is a version of fusion. So what we're trying to do is to achieve this fusion energy in a reactor on Earth. The easiest fusion reactor we can think of is between two isotopes of hydrogen. So we have deuterium and tritium, they're basically hydrogen isotopes. And if you combine these two, you get helium. Helium is the light element as well. And you get 18 MeV of energy and neutrons that comes out of it. So the aim is to fuse these hydrogen atoms and make helium and a lot of energy. And this doesn't require much resource. As you know, hydrogen is in water. You can take it out of the water. So this has the potential to solve a lot of our carbon emissions and other issues. So we want to do fusion on Earth. Well, why don't we use the same method that sun uses for fusion? Sun uses gravitational compression, right? There's a lot of mass. It's billions of times bigger than the world, and that compression of gravity induces the pressure needed to achieve fusion. Well, we can't do that on Earth because you need the size of a sun. So what we can do instead is magnetic confinement. That's the most developed technique for fusion. So as you know, if you have a magnet, South Pole and a North Pole, and you have a magnetic field this way, electrons and ions kind of gyrate around that magnetic field. They're confined in this region. They don't fly off in this direction. But what happens is that at the end of the day, they hit the edge. So they hit the magnets. So this is not ideal, obviously. What you can do is take this magnet and turn it into a donut. So that's what, has been done before. Russians invented tokamak. So it's basically a torus with magnetic fields around it. And you have the plasma confined inside. Without getting into details, that's basically the reactor that I'm going to be talking about. It's a tokamak, plasma inside, magnetic fields outside, and using magnetic fields to contain the plasma so they don't drift out. There's been a lot of progress that's been made. This is the years versus the fusion power. We went from negligible powers to megawatts of powers in around 2000. And if we look at the future, we have ITER. It's a collaboration between US, EU, China, India, Russia, and South Korea. It's the largest research endeavor in the world. It's 30-40 billion dollars and counting. And it's huge. If you look at this, I'll go back here. So this plasma here is inside this donut hole. And this is about 10 stories high. You see a person here, and that's an ITER fellow. That's me sitting next to this, standing next to this. You can see the size of this. It's huge. It's going to produce 500 megawatts of power, 10 times more than what's put in. And that will be the first step to making a reactor. What we see nowadays, we have private fusion companies in addition to government entities. There's about 50 private companies now. Billions of dollars are being invested, and these are some of the companies. And I work with many of these companies, try to help them out as much as we can. So we'll see who's going to get there first. But there's a lot of excitement and energy. Hopefully we'll get there sooner rather than later. So what are the issues that we face in a reactor, fusion reactor like tokamak? So one of the things that we have is instabilities. So this is a tokamak disruption from CMOD. So you're going to see the plasma is now formed. And you see the fireworks. Those fireworks, I don't know how the video comes through. Does the video come through there well? If you look at it,
Yes.
Yeah, you see the sparks here. So the plasma was doing okay, and then it hit the wall. There was an instability, and the moment it hits the wall, pieces of metal starts flying, and you can see that that's not a good way to run a reactor. You might blow a hole in it. So we want to avoid these type of events. So how do we do this? So normally, this is the cage that the plasma lives in. This is the plasma. Plasma is stable normally, but sometimes, in seconds time scales, it becomes unstable. The problem is that once it becomes unstable, the growth rate of these unstable modes is very fast. It's millisecond time, much less than a second. So then at this stage, you can't control it. And basically the plasma hits the wall. It's an example of a damage at jet, and you melt it or do something to it. So what you need to do is to avoid getting unstable, because once it's unstable, it's hard to do anything about it. It's too fast. So we have to stop this for ITER and future reactors. So for that, you have to stop this unstable equilibrium, how to get there. So if you avoid that, then you don't have this instability and you don't have any problems. So to do that, these timescales are quite fast. So you can't have, sometimes people ask, why don't you have like a human operator like steering the plasma? Well, unfortunately, it's too fast. Our eye-hand coordination will not be able to control a plasma because it's sub-second. So you need a computer system and intelligent algorithm to see what the plasma state is, how is this doing, and avoid any instabilities coming through. So that's perfect job for machine learning control for fusion. So the physics is very complicated. The fusion plasmas are very complicated, These are, and there's a lot of diagnostics. We'll talk about this. There's going to be less in the future, but still, you have many diagnostics. And it's a prime target for machine learning control design. So when we talk about control, we have these desired outputs. So desired output can be power, no disruption, etc. And then we have a controller. This is the plant is the fusion reactor, and you get the output. And then you have a measurement system. It's like our eyes that loops back. So basically, we see with our eyes, that's the measurement, and we have the hammer to control the plasma. So first, I'll talk about the eye, then I'll talk about the hammer. So for the eye, we're lucky in the current fusion reactors, we have huge amounts of diagnostics. There's probably about 100 diagnostics here. Like this is motion stark effect, this is pyrometer, there's a bunch of these. But in the future reactor, we're not going to have as many because, we want to keep the cost down and there's neutrons flying around, so you're not going to be able to run this many reactors. So how do we then obtain robust and minimal diagnostics for a fusion reactor, right? Because first you need the eye, so we got to get that sorted out. So in D3D we have this, and either it's going to be like this, and demo it's going to be producing electricity. So nuclear environment requires minimal diagnostics. Because of nuclear environment, you have faults and failures. So some diagnostics are going to fail. So how do you become robust, and what is the minimum required diagnostic set? And for this, we say machine learning to the rescue. Let's see what it does. So first thing is plasma state. What is it? So I showed the reactor. I showed this donut here, right? This is inside it. There's this donut plasma. So if you take a cross section, it looks something like this. These are concentric rings of confined plasma. So we usually think of it as a shape of this. So this outside shape, that's this. You need to know what the outside shape is, and you need to know these 1D profiles. So from the core of the plasma to the edge, because this transport around here along this direction, all the temperature here is about the same. So you just need this temperature from core to edge, for example, TE going from core to the edge. So 0 is the center, 1 is the edge. So plasma state, to simplify it, is this shape plus 6 profiles. 6 profiles are the pressure, electron temperature, ion density, etc. So how do we find this? Well, there is some, if you take Maxwell's equations and simplify it and do some magic, you get into some sort of a PDE. It's very nonlinear that specifies the plasma state. So this is the Gratz-Raffaello equation. It's a nonlinear PDE. So that's the fundamental equilibrium equation. And then we have a bunch of diagnostics. We have magnetics out here. We do some measurements of Thomson scattering inside the plasma with lasers. We have some probes. We have charge exchanger combination. And then the aim is to bring some sort of a least fit sort of way all this information and fit this PDE equilibrium that gives us the best match with the measurements, right? So basically, we go from measurements to plasma state. It's a reverse problem. It's called the reconstruction. So historically, this was done by, like I said, if EFIT, it's a Gratz-Raffaello solver, solves that PDE. And you go from diagnostics here. These are all the diagnostics. You go to the physics-defined zero-D profiles. And then you have some physics-based prediction. So first, I'm going to talk about the surrogate model. So basically, we take this module that takes the diagnostics and gives you the equilibrium and turn it into some machine learning-based inversion. That's kind of, if you know machine learning, this is, relatively easy. Everything is relatively. So what we have there is what we call EQNet. So it takes the plasma shape prediction using surrogates. So we have, as I said, all this diagnostics, and we have an equilibrium code that works offline. So we make a surrogate machine learning model that runs in real time. And we can run this really fast, inferred in some milliseconds. And it turns out to be as good as the offline analysis, solving this nonlinear PD offline versus online. You see they're basically on top of each other. We get the same shape. But it turns out it's much better than a real-time version of this PD solving, because when you're solving in real time, it turns out it's very hard to solve this big PD in real time. So you make a lot of simplifications, and it takes a lot of time to solve this even the simplified version. So what happens is the first is that the real-time EFIT, the RT EFIT here, I'm giving thumbs up. I love the automatic thumbs up here. So there's a bit of a time lag, the real-time system. So that's bad because time lag kills the control. That's number one issue. Number two, you get these really ziggity-zag unconverged results, and sometimes you get a plasma that looks like a beam, which it isn't. But if you do a machine learning to find a surrogate model for your PD solving, you get perfectly nice equilibrium reconstruction, and you can do much better control because you lose this 5 millisecond delay and all these weird jumps. And that allows you, this is NSDX, to control NSDX, this is simulation, to much higher elongation stretch. And that elongation is good for better confinement, better fusion. So this is work that my student did for NSDX. Now he's working for CFS. He's doing the startup. He did the startup for CFS. Okay, so now we got the shape. We got the shape from the using machine learning surrogate model. Now we need to find the profile inside from the core to the edge. So for that, we develop consistent automatic equilibrium reconstruction called CAKE. So basically, this is the hard part of every work. We just take all the experimental data and develop the code. They can automatically convert that for data into equilibrium and profile. So for example, here is the density. These are some other parameters. So you can see the density is a function of this, and it solves the equilibrium, gives the current here and the pressure using the experimental data. This was done by Anthony. Then the easier part is making a surrogate model out of it. So this is cake here, and we made a surrogate model out of it. It takes and the details being details is machine learning, but you get all the profiles that you need. These are the 6 profiles, like the temperature and the density and so forth. And you say, that's nice. Okay, you're showing another surrogate model. That's nice. But one nice thing about this is that it's very robust. Here you see the real-time alternative. It basically doesn't go to the edge, the green one here. But RT cake, the real-time KNN, the neural net version, works perfectly well. And you say, okay, that's fine, but what is interesting about it? Well, what is interesting is we can train now this inversion from experiments to the diagnostics into the profiles by throwing a lot of uncertainty to the reconstruction. So what we did is sometimes diagnostics fail. In a reactor, they're going to fail. So you can run the machine learning algorithm so that you sometimes turn off some of the diagnostics. You say, oh, well, it failed. Some of them fail, some of them unfail. And then you put more noise. Sometimes they become more noisy than usual because you have this opportunity to train for a long time with all this different garbage of data that you can put in there. What happens is that the algorithm learns that if something goes wrong with the diagnostics, it's supposed to ignore it and use the other information to infer what that diagnostic was supposed to give. And lo and behold, we tried this for the first time, literally first time in the machine. And this is what happened. This is the Thomson scattering. It looks very nice and flat. Well, Thomson data, this is the density and temperature. It's never like this. It basically was someone jammed the door while they were putting the cable. Cable got jammed to the cable cabinet, and it was it wasn't unresponsive. So you just got straight lines. But even with that, we were able to find the density and the temperature in real time because the algorithm is trained to know when things fail and still do the best it can. And it's able to find all the other properties. And funnily enough, second shot, another diagnostics, this charge exchange recombination is all showing 0. It's not 0. It just happens that the data acquisitions didn't work that shot. And you can still find this is ion velocity and temperature. So it's able to find these things even though you got no data. So that's the beauty of machine learning, is you can train it to be robust to all sorts of weird stuff, which is very hard to do if you're training a regular old Kalman filter, for example. Okay, so that's the standard. We take the physics codes and turn them into surrogate models. Good, but there's some nice things. Like I said, you can get robustness, failure, and so forth. But another thing you can do is we said, okay, well, why do we have to use this physics codes? Why do we have to use this diagnostics physics code, outputs? So now that we are in data, why don't we just take the data and try to predict the data itself? Because all these physics things that we're looking at is made up by humans. It doesn't really exist in life. It's the only thing that's real is data, right? Diagnostics. So we said, okay, let's just throw out all the physics and let's predict plasma state to be the diagnostics. Just, if you can predict what the diagnostics are going to be, then you know what the plasma is anyway. So there's not much of that. So we took the controls and diagnostics and try to predict the future diagnostic. So how does that go? So I'll show you in a couple of examples. So one of them is we have the CO2 interferometer here. So we have 4 channels, V1, V2, V2, and R0. So we were trying to see if you take 3 of these channels and develop a neural net, can you predict the 4th one? So this is the measured and this is the reconstructed. So it turns out you can do a pretty good job of reconstructing this channel. So why is this interesting? Well, like I said, in a reactor, we are not going to be able to put many diagnostics. What this tells you is maybe instead of putting 4 channels, you need 3 or maybe 2. So you can do this comparison and find which channels you're going to need, which you're not going to need. So then we said, okay, let's try to look at from one diagnostic to another diagnostic. So we have interferometer, ECE here, electron cyclotron emission, 40 channels, and then we try to predict the CO2 interferometer. So these are totally different, independent diagnostics. They have nothing to do with each other. But it turns out there's enough information here to reconstruct pretty much the main points of this diagnostic. You see the trends here. You can see the alpha and eigenmodes here. All these things are pretty much good. And what we showed is that using this reconstructed image, we can find the modes that we need, that we are interested in, pretty much perfectly. So this tells you maybe you don't need 2 diagnostics, 2 of these together. You need only 1 of them. So this allows you to look at all the diagnostic sets and say, rank them and say, these are the ones we need, top 5. We don't need all the 50. Okay. So then another thing is some diagnostics are very expensive, but very good. Like Thomson scattering is very expensive. It's only 50 hertz, so every 20 milliseconds, but it gives you nanosecond correct measurements at inside the plasma. But we have cheaper diagnostic like ECE, that's 500 kilohertz or a megahertz. So we thought, okay, can we use this 500 megahertz measurement to interpolate between these Thomson points? So what can you find? Basically, it's super resolution, if you heard about it. We want to do super resolution Thomson. And we trained that so that ECE here is trained, map is trained to find Thomson at this point, and it can interpolate in between. And this worked out quite well. So here is the Thomson scattering profiles. So we get 1 megahertz Thomson scattering profiles. That's really nice. And it turns out our upsampled and the data looks really nice in many ways. So we can then take this and look at physics with it. So we can look at 1 megahertz physics that we weren't able to look before. And we have hopefully a new paper coming up on this. And here's what it looks like. This is an Elm semi-vat. It doesn't matter. This is what a single time in time data looks like. So this is the Thomson, these crosses, but we can make a 500 megahertz version here, which follows pretty much identically, but it can find all the details, structures here. Like for example, here you can see what happens right before this event, which you can't see in the regular slow system. Okay, so that's predicting the state. Now, once we know where we are, we want to see how the plasma evolves. That's the dynamics. I'm here at time t. I want to see what the future is going to be. So for that, we have the plasma state, the history of the plasma here. And then we say, okay, I know the history of the plasma, and I know what I can put as the controls in the future. So this is history, this is future. Then I say, okay, if I take this, can I figure out what the future state is going to be? So this is the current state. I want to predict the future state, given the controls. And we did that based on looking at all the historic data and developing neural net. And here's the example where it works really well. I mean, it's extremely well. So we have the time t here, and this is 200 milliseconds later, the neural net, the prediction versus reality. So it's able to predict how plasma is going to evolve without any physics. So this has no physics, all data-based. And I'll show later that this ends up being better than the simulations. So this is, then you can take this model, now a model of plasma, and I can integrate it forward. I say, okay, start a plasma here. I put in beam power, and this is the beam power I'm putting. I put some currents, and then I can see what the profiles are doing. Rotation goes up, density is increasing here. It has this profile, temperatures here, and so forth. So I can predict what the future. So basically, I have now a full model of the plasma. It's like a game. I can play with it. And then I can say, what if I increase the beam, reduce the beam and increase it again? So I can see rotation going up and down, temperature is increasing and reducing. So now I have this model that I can play with. Then you say, well, okay, this is great. You use all the data, do a great job, or a reasonably good job of predicting how the plasma is going to evolve. But, well, when we try to predict a different machine, let's say we want to predict ITER or a fusion reactor, machine learning is not good at extrapolating. So maybe then we need fusion experiment simulations. So you say, okay, I'm going to add simulations to this. This is all this, plasma simulations kind of work out. It's a bit complicated figure. And then other thing you can say is, okay, I'm not going to use one machine. I'm going to use multiple machines. So we did that. We're using ASDEX here, very close to D3D. And this is ITER, by the way. This is where we are. So we said, okay, if we take two machines, data from two machines and simulations, and put them all together, how much better way can we do, right? I was talking about just machine learning before with data. So there's a lot of work here. I mean, this is a thesis project. This is the single slide of a thesis project that was presented last week when my student graduated. So the outcome is this. Outcome is that experimental data dominates. It's 65% of the information. So let me try to say. So for example, here you see that this is TI prediction error. And this is for machine learning from data only. This is some physics-based and other physics-based different types of physics inputs here. And this is the meta, which is the combination of physics and experimental data. And obviously the combined does much better. But if you look at it, it's dominated by experimental data. It turns out the simulations are helping, but not as much. And if you look at the experimental data, it's more interesting. It's the experimental data of your own machine is dominant source of information. So what this is saying is when you start a new reactor, you might be better off just trying to develop your own model as you're going up than trying to rely on physics or other machines. So this is very interesting. So once you find these plasma evolution, then you want to detect these events that you don't want, like disruptions and so forth. So for that, we developed a bunch of machine learning algorithms. So here is again diagnostics, ECE. There's 42 channels from core to the edge. and this is what they look like. You can enhance the spectrogram using machine learning, and then you have RNN, in this case, predicting different type of alpha eigenmodes. TA is like toroidal alpha eigenmodes, reverse Urago eigenmode, etc. So how does it work? So this is what the raw data looks like. This is the clean data using autoencoders. And you see that here I have an RSAE. I predict there's an RSAE and TAE. This is at the edge, raw was the edge. Oh, this is moving inwards. It says this mode moving inwards in time. And now it disappeared. So it moved inwards and then it kind of just died off. So you can now detect and predict these modes as they come out and where they are. Not only predict these modes, but see where they are. Okay, so now I showed you some examples. There's more stuff of how I can predict the state of the plasma, the future of the plasma, and events that might happen. So now we're in a state where we can use this for control. How do I use machine learning for control? See how we're with time. I think we're fine with time. So I'll give you some examples. The first one is for edge localized modes, is edge bursts. So this is an example of what happens at the edge of the plasma. This is the edge of the plasma. And these blobs basically are coming down in the simulation and they hit the wall. So this is what happens. These blobs are coming down and they hit the wall. When they hit the wall, the blobs of energy damages the wall, damages the diverter. So we want to stop that. Well, how do we do that? If we use 3D perturbations, these are like panels here, just if tiny bit of 3D perturbations, to simplify a bit, basically locks these modes so they don't kind of like rotate and hit down in a way. They're kind of just here, they're stationary and they're happy. So, this is something that will be used for ITER. Then we want to control this. How do we do it? So these spikes that you see are those edge localized events. And if I apply some 3D perturbations, this is the amplitude of that. At some point, I get rid of them. And I can keep it there. But the problem is that my confinement of the energy is kind of going down, which is not good. So then I say, okay, well, I can maybe reduce the 3D perturbations a bit. And I'm happy now, my confinement is going up. But at some point, I get out of the suppression regime. The instabilities come back. So then you need some sort of an algorithm to figure out how to go in and then use this hysteresis. So you're going in at let's say some 1 amp, but you're going out at a much smaller amp. So use that hysteresis to kind of reduce the amount of perturbation I need and have higher confinement. So we wrote this algorithm, and this is an example from K-star. So what we have here is the 3D coils are, suppressing the elms here, and then they go down, and when they see elms coming up again, these modes goes up again, and then it goes down when it sees it coming up, and then it kind of adjusts itself and automatically adjusts itself so that now there is no edge localized modes, but my confinement here has gone up. So beta n went down here, but it's now way up. It's basically where I started. So that's the idea. It gets a bit more complicated. I just showed you a simple example. For that, we have GPECnet. Basically, it looks at how the 3D perturbations affect the plasma and how adjusting the different coils and so forth affect the plasma. So without going into the details of that, we put this system on K-star on ND3D and show that basically by automatically we get elm suppression with high confinement. And you might say, well, okay, what is the end result of this? The end result is this paper in Nature Communications. So this is fusion gain versus H98. This is confinement. This is how much fusion power you would get out, sort of like, the merits for that. And this is D3D data here. And these are our controls. So it shows that we basically have highest fusion gain and highest confinement factor by using this adaptive Elm control that uses machine learning. And here's the K-star data, and here's our shots. So they're way outside of they're the best confinement shots as well. So you can show that the systems are helping you get the highest value achieved in two machines, on K-star and on D3D. So it's robust. And then you can say, okay, why am I doing one predictor for one machine learning for measurements for my eye and another for my hands for the control? Why don't I put them together like a human? I have the brain and the hands, you know, basically make a whole human. We can combine it together. If we combine it together, then we can do full machine learning control. So this has been done in you know, you've probably seen DeepMind. This is AlphaStar. So basically you say, here's the game. It's like AlphaGo too. Here's the game. And you say, go play the game. And as it's, you know, playing the game, the neural nets kind of learn how to play the game better and better and better. And after, you know, some billion GPU hours, it gets really good at playing AlphaStar video game. So how does this work out? So what you need is an environment. So in this case, this would be the video game, right? And you need some action. The actions are what you're putting in: go left, go right, you know, shoot some weapons or something. And then you have observations, rewards. In this case, it might be the screen. So you see the screen, you know, some things are dying or whatnot, or you're seeing that your points are going up. Then in this, then you throw in your agent, AI agent, artificial intelligence agent, and by playing this game, it learns how to do it, and it gets really good at winning it. So in our case, we have plasma observations, plasma state, right? And then we have actions that we take, which is, you know, I'll talk about it: neutral beams, electron cyclotron heating, magnetic currents, etc. And then our reward is going to be the fusion gain. Or we don't want instabilities, no tearing instability. And so this is what we put on D3D. So this is what it looks like. So if tearability is this instability, so if you have too high instability level, the plasma just goes totally unstable and you lose the plasma. Plasma literally just goes to hit the wall. And to avoid that, you need the actuators to avoid the stability limit. So there's a stability limit here. If you get close to it, you say, no, 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 I don't want to go there. And then you go up, oh, it's too bad, and then kind of find your way around it. So you need to find this optimal path in time for your actuators so that you can avoid all these instabilities and have highest confinement. So in real life, this is what it looks like. This is the measurements. We have all these diagnostics, magnetics, Thompson scattering, etc. And we have these actuators with what we control. This is the heating systems, ions, magnetic control, and so forth. And this is the agent. It's learning. It's playing the game offline and then online. As new information is coming in, the reinforcement learning is updating the control. And this is the result of that. This is the shot without the control, the black one. And that one, we have this instability limit. It's invisible, and it hits that somehow. And the plasma current goes to zero. Basically, the plasma just dies. In the reinforcement learning control system, this is the controls. This is the magnetic control. This is the beam control. And it's able to avoid this instability, and it's able to achieve highest possible confinement without any instability. So this is what the fusion gain in time looks like. And the red places here are higher probability of instabilities. So fusion gain goes up, and it sees that you want to increase this, but you don't want to hit these limits. So it goes down a bit and it goes up a bit. So it kind of keeps you away from the instabilities with highest possible fusion gain. Another interesting thing that we do is large language models for as a co-pilot for fusion reactors. So you probably know ChatGPT and so forth. I'm not going to dwell on this too much. But the idea is that we have local data, and we use that local data to train language model. So we have logbooks, we have papers on plasmas, we have you know, all sorts of written documents. If we put this all together in a large language model, you can have a model that can tell you answer your questions, and it will help you as a co-pilot. So we trained this for D3D. I think we have like 1,000 papers and all the logbooks that are possible. And this is what you get. So you ask questions and get answers. So you say, how do you quantifiably determine a tearing mode? And it says, well, you have to look at the spectrogram. You can look at the backscattering measurements. You can look at the CPS and all these other things. And it tells you what to do. And then you ask it, who should I get as my physics operator? And it says, based on historic, Al Hayat is a good operator. Maybe you should ask him how to do it. And you say, how do I turn on the machine learning profile prediction control, design control, and PCS? It says, turn on the algorithm selection, go to shot profile predictor, and all that stuff. So it's not an amazing thing, but it's for someone who doesn't know anything. This might be helpful, just getting you ramped up and just looking up things like, where is this button? And it tells you scroll down here, and on the right you're going to see that. As the highlights of this talk, we're coming to the kind of end of this. I think I was asked to give like a 45-minute talk. I can talk a bit more, but first thing I'll tell is that we have this, this is the Nature paper that Egemen was the first author. We show that you can have reinforcement learning control and achieve instability-free operations at D3D and fusion reactors at high performance. And this is the performance. And we've shown that you can get the highest confinement fusion gain values without edge disturbances at D3D and K-star with machine learning control. So these are experimental data. And we've shown that we can do robust reconstruction of the equilibrium and the state of the plasma using machine learning techniques. And that, I thank you. I can do it again, maybe. Oh, this is what we have. Maybe I'll try to go back. Let's see if I can. And, we use NVIDIA GPUs, and they put us on the NVIDIA event. So this is the tokamak. This is the outside. This is the plasma. And it's kind of a cartoonish version of what we do for avoiding instabilities.
And paving the way towards unlimited clean energy for us all.
So this is the instability. It's like an island there. And then you just cancel it. You get rid of it. Anyhow, so that's one thing we do. Yeah, I can take a bunch of questions. It's 43 minutes. I think I'm close enough. There's other things we do too, but I'm not sure if it's worthwhile. So we do a lot of image-based analysis. So we have some sort of image-based detector for this is camera-based detector that we do work with Livermore collaborators, Frescati, Livermore collaborators, and we can use the cameras to detect what the plasma state is. And we put that in on D3D as well. So we do some image-based analysis as well. Okay, well, thank you. If you have questions, I'm here.